Hello there, Mr. Sutton here, bringing you the AB Calculus 415 Extra Practice number 3 solutions on advanced related rates. On this no calculator problem, we have a person standing 30 feet from point P, watching a balloon rise vertically from a point, and the balloon is rising at a constant rate of 2 feet per second. We want the rate of change in radians per second of this angle right here, theta, at the instant when the balloon is 40 feet above point P. So this is interesting on a number of levels. For one thing, we're being asked for one rate of change and we're given another rate of change. So this is a related rates problem, meaning we're going to have to come up with a formula that ties all of this together and then differentiate with respect to time to get at these rates of change. Another thing that makes this interesting is we're looking at a rate of change of an angle. We usually look at rates of change of kind of distance sort of dimensions, so this angle aspect adds a little bit of spice to this problem. All right, so what is an equation that ties all of this together? Well, we have really three quantities going on here. We have the angle itself. We have this, I guess you could call this like an x value. It's a horizontal sort of distance. And then we have this vertical distance involved in the problem. They didn't really do much or talk much about the distance between the person and the balloon itself. So this hypotenuse, if you will, isn't really part of this problem, but certainly this y value here is. So I'm going to label this y just so we have something to refer to it with. Now, a good relationship between these, since this is a right triangle, we can use some of your SOHCAHTOA math. We have the opposite side from the angle and the adjacent side. So this is going to be TOA, tangent equals, or tangent of theta equals opposite, which is y, over adjacent, which is 30 in this case. So this is an equation you can use to tie everything together. Now, before you go ahead and just take the derivative with respect to time, right now, if you do that, because you're going to have to multiply each of these by a d, whatever the variable is, over dt sort of tail, that means that if you take the derivative right away, you're going to have secant squared of theta times d theta over dt, which is fine because you're solving for d theta over dt in this problem, but then you're going to have to figure out what this angle actually is. And since this is a no calculator problem, that's going to be kind of annoying. So another way to do this problem would be to isolate theta before you take the derivative. And we can do that if we take the arctan of both sides. So I can write this as arctan of, or actually just theta equals arctan of y over 30. And now if I take the derivative, I don't actually need to know what theta is to solve the problem, because I'm just going to end up with d theta over dt on the left side. Now arctan is a little bit more annoying of a derivative than just y over 30, but we at least can plug numbers in for y and deal with it as we come to it. So derivative, this is going to be a big chain rule here. Derivative of arctan of something is going to be 1 over the something squared plus 1. So 1 over y over 30 squared plus 1 times the derivative of the inner function. Well, the derivative of y over 30 is 1 over 30 times the derivative of y, which is dy over dt. So everything is a function of time here. At this point, it's time to start plugging things in. So for d theta over dt, we don't have to plug in anything because that's essentially what we're looking for, the rate of change in radians per second of our angle. For the y value, that's the value of this y value at the specific time this problem takes place. And they told us that. That's this 40 feet right here. And for so let's plug in 40 for y. And then 1 over 30 is just still what it is. dy over dt, that's the rate of change of y. They said the balloon is rising at a constant rate of 2 feet per second, so that means dy over dt is 2. And at this point, we just have to go through and simplify because, well, all the answers are simplified. So this is where we're hoping you paid attention when we were teaching you about fractions and exponents and all the rest of it. 40 over 30, we can reduce that to 4/3. And if I square that, that's going to be 16/9 down there. And we have a 1 over 30 times a 2. We can reduce that to be 1 over 15. I mean, why leave it hanging around, right? Now, let's reduce this first fraction a little bit more. 16 over 9 plus 1, well, that's really 16 plus 9 over 9, or 25 over 9. And 1 over 25 ninths is going to be the same as 9 over 25, just multiply by the reciprocal. And we can go a little bit further. This 9 and this 15, we can reduce that to 3 over 5. So now we've got 3, if we multiply straight across, over 125, which gives us answer choice B. For this problem, we have two straight roads intersecting at right angles, and a car traveling south toward our intersection, while a radar-monitored speed sign is a quarter mile east of the intersection. And then the speed sign provides both the distance from the sign to an approaching car and the rate at which the distance between the sign and car is changing. All right, so before we do anything else, let's draw this situation here. So we have two roads that are intersecting, like so. And let me just draw another line here, because this is going to be a triangle. We basically have a car here coming south towards this intersection, and we have a sign over here to the east, to the right, I guess, depending on which way you're facing, that is a quarter mile east of the intersection. So this side of the triangle is not fixed because this is essentially the distance between the car and the intersection. This side of the triangle, however, is going to be fixed because that sign is not moving. It's still going to be a quarter mile east of the intersection no matter what the car is doing. And then, of course, this hypotenuse then is going to be changing if this side of the triangle is changing. So this is our situation, and I'm going to call this y here just so we have something to refer to the distance between the car and the intersection. So moving forward now, at a certain time, the speed sign shows that the car is exactly a half a mile away from the sign. So we have like an instant value here, and I'm going to call this z just so we have something to refer to this distance. We have an instant value here of 1/2, and that the rate at which the distance between the car and the sign is decreasing is 60 miles an hour. So this rate of change, dz over dt, I guess, is going to be 60. So we want to know which of the following is true about the distance between the car and the intersection. And these are all talking about the rate at which this distance is changing. So we're basically given one rate of change for z, and we're asked about the rate of change for y. And we're also asked whether that rate of change is a decrease or an increase. Now, since our car is moving south, I mean, if you can visualize this, then it probably makes sense that this distance is decreasing. So that already most likely eliminates choices A and C, which talk about the distance increasing. I mean, you never know. We have to crunch the numbers, but it makes sense that this should at least be a decreasing quantity. But let's do this whole thing out. So we have a related rates problem here. We need to set up an equation that ties all of these quantities together and then take the derivative with respect to time. So a good equation to use, since this is a right triangle essentially, is going to be the Pythagorean theorem. So we can say 1/4 squared plus y squared equals z squared. And now we can go ahead and take the derivative with respect to time. Since 1/4 squared is a constant, that derivative is 0. Derivative of y squared, that's going to be 2y times dy over dt. Derivative of z squared is going to be 2z dz over dt. So everything here is a function of time. And then we need to find quantities for pretty much everything except dy over dt. That's the only thing that we don't know in this problem, or at least that we're trying to solve. So for the y value, well, we actually don't know what that is. We know that the z value at a certain point in time is going to be 1/2, but the y value, they didn't tell us. Fortunately, if you know what the z value is at a certain point in time, I mean, you've already got this x value here, so you can use that in your Pythagorean theorem to figure out the value of y. So we can write that y equals the square root of z squared minus 1/4 squared, or basically 1/2 squared minus 1/4 squared, because that's what our z value is at this point in time, is 1/2. So let's see here. This is 1/4 minus 1/16, or 4/16 minus 1/16. That comes out to 3/16 inside that square root. And the square root of 3/16, we're going to have to simplify that a little bit more, and that's going to be radical 3 over 4. Okay, so we've got 2 times the y value, root 3 over 4. dy over dt, again, we don't know what that is. We're going to leave it that way because we're solving for that. And then z, they already told us that was 1/2, the distance at this point in time between the car and the sign. dz over dt, that's the rate of change in the distance between the sign and the car. And they said that that distance was decreasing at 60 miles an hour. So we're going to write -60 for that to signify what's happening there. And let's clean this up a little bit so we can solve for dy over dt without a calculator. So we can reduce this here to be radical 3 over 2, dy over dt. Over here, the 2 and the 1/2 conveniently cancel, so this is just -60. And now solving for dy over dt, we multiply both sides by 2 to get -120, but then we divide by radical 3, so we end up with -120 over radical 3. The units are going to be miles per hour, in case you were unsure about that. Since we have a negative rate of change for this quantity here, that tells us that the distance between the car and the sign is decreasing at a rate of 120 over radical 3 miles per hour. Choice B. For this problem, we have a water tank in the shape of a right circular cone, as shown in this figure. Diameter of the cone is 10 feet. The height is 15 feet, and then we have the shape of the water in the cone, which, because it conforms to the shape of the container, is also going to be conical. We're talking about a radius that's labeled as R, and the height of the water we're calling H. So, at noon, water's leaking from the bottom of the tank at a rate of 12 cubic feet per hour, and the volume of water in the tank is 27 pi cubic feet. At noon, so the same time, we want the rate at which the height of the water, so that's h, the rate at which h is changing. And they give us the formula here of a right circular cone's volume. Okay, so to get at this one, we're talking that we have a rate of change in the volume that we're given, and we're asking about the rate of change of the height of the water. So since we have multiple rates of change going on, we need to basically this is a related rates problem. We have to write a formula that ties all of these quantities together and then take the derivative with respect to time so that we can talk about all these related rates of change. Well, a good formula to start with would be the volume formula they gave us here, because volume is changing and we are also talking about height, which is in this formula. So we'll start there. Now, the tricky part about this problem is that the radius is also in this formula, and they didn't really give us any information about the radius other than the radius of the entire tank, which is not necessarily the same as the radius of the water that's in there. So a good move here would be if there's a way to swap out this r for some expression that has h's in it. That would make our lives a little bit easier when it comes time to actually plug in quantities for these different variables. Okay, well, to do that, we can actually set up a little bit of a ratio here between r and h, because the ratio between r and h, if you just think of this as like a triangle, it's going to be the same ratio as between the radius of the entire tank and the height of the entire tank. These are essentially going to be two similar right triangles that we have going on. We can say that r over h is the same proportion as, well, the r up here would actually be 5, so 5 over 15. Which is to say we can say that r is equivalent to 5h over 15, or if we reduce that, h over 3. So this r right here, I can actually replace that with 1/3 h quantity squared. Now the reason that I substituted for r rather than isolating h and replacing stuff over here with r's is because they gave me a little bit of, or they were asking about the rate of change of h in the problem. They didn't really give me any information about h or r, but at the very least we're asking about the rate of change of h. So it would be helpful if the formula that I'm working with has an h in it instead of an r if I have to choose between those two variables. Simplifying this a little bit now, this is going to be 1/9 h squared multiplied by the 1/3 already out there. We have a 1 over 27, we have a pi, and we have an h cubed. So this is our final simplified volume formula that we're going to be working with for the rest of the problem. Okay, let's go ahead now and take the derivative of this whole thing with respect to time. So derivative of volume, That's going to be dv over dt. And then over here, using the power rule, the 3 and the 27 reduce to a 1 over 9. So we have pi over 9 h squared times dh over dt. Height is also a function of time in this problem. At this point, it's time to plug in for what we know and leave what we don't know unplugged in. So we're solving for dh over dt. They want to know the rate of the height of the water. So we're going to leave that the way it is, but that means we need to know what dv over dt and h are on this problem. Well, dv over dt, this is the rate of change of the volume. Now, they said that water was leaking from the bottom of the tank at a rate of 12 cubic feet per hour. Since we're losing volume, this is going to be a negative rate of change, so we can write negative 12 for dv over dt. And for the height, well, they didn't actually tell us the height, but they did tell us that at noon, the volume of the water in the tank is 27 pi cubic feet. So just looking at our formula here, v equals pi over 27 h cubed, if we know the volume, well, there's only two variables here, volume and height. So if we know the volume, we can figure out what the height is at that time as well. So I'm going to do that over here. I'm going to write 27 pi, the volume, equals pi over 27 times h cubed. And this equation is a little bit beastly to solve without a calculator, but we can do it. I'm going to start with the low-hanging fruit. I'm going to divide both sides of this equation by pi. So I can write 27 equals 1 over 27 h cubed. And at this point, just typical algebraic sort of process, I would usually multiply by 27 on both sides, but I'm not really sure what 27 over or times 27 is, and I don't really feel like figuring that out by hand. So I'm just going to take the cube root of both sides right now. I would usually wait, but I'm going to do it now. So I'm going to have 3 on the left side and 1/3 h on the right side. And now I do know what 3 times 3 is, so that gives me an h value of 9. So I can plug that h value of 9 in right away. This is now going to be pi over 9 times 9 squared, dh over dt. And let's simplify this a little bit now to solve for dh over dt. So this is really pi over 9 times 81, which I can cancel out the 9 down here. This is just going to be 9 pi dh over dt on the right side. And then solving for dh over dt, if I divide by 9 pi, negative 12 over 9 pi can be reduced to negative 4 over 3 pi. So what does that mean? That means that our height, our altitude, I guess, of our water is going to be decreasing at a rate of 4/3 pi, and that's going to be in units of feet per hour. So that's going to be choice D. For this no calculator free response problem, the setup is that we have ship A traveling due west from Lighthouse Rock at a speed of 15 kilometers per hour, and then there's this ship B up here traveling north away from the lighthouse at a speed of 10 kilometers per hour. So this ship right here is going left, so this x value is decreasing on this triangle. This ship up here is going north away, so this y value is increasing. And then the overall triangle is changing as well. So first task on here, we want to find the distance between ship A and ship B when x is 4 and y is 3. So we're trying to find this distance here. Well, this is just essentially Pythagorean theorem. You're just finding the third side of a right triangle. So we'll just use Pythagorean theorem. We can say that this is going to be the square root of 4 squared plus 3 squared, which is just the square root of 25, which is just 5. Careful, though, we need to put units on this. And they told you what units. It's going to be kilometers. So 5 kilometers. Done. For this part of the problem, they want to find the rate of change in kilometers per hour of the distance between the two ships at the times when x is 4 and y is 3 kilometers. So we've got rates of change of x and y, and we're asking for a rate of change of this other quantity, which, by the way, I'm just going to refer to as r. I guess I could also call it z. But in any case, we've got multiple rates of change, so this is a related rates problem. We need to set up an equation that ties all these quantities together and then differentiate that with respect to time. So a good equation to use here, since we're dealing with a right triangle, is pretty much what we used in part A, Pythagorean theorem. I'm going to write x squared plus y squared equals r squared. None of these are fixed values, so these are all going to be variables in my Pythagorean theorem. And now I'm going to just take the derivative of everything with respect to time. So derivative of x squared, that's going to be 2x times dx over dt, plus now we've got 2y plus, or times dy over dt, equals 2r times, of course, dr over dt. And what am I solving for here? I want the rate of change of the distance between the two ships, which is r. So I want dr over dt. That means I need to know what all 5 other things are. Well, x in this case, they said was 4. They gave us that. Dx over dt, that's the rate of change of x. Now, they said that ship A was traveling toward Lighthouse Rock at 15 kilometers per hour. That means that this distance here is decreasing, so this is a negative 15 for the rate of change dx over dt. Now, the y value they said was 3. That's just the distance. Since ship B is sailing away from Lighthouse Rock, this y value, this rate of change is going to be positive because this y distance is increasing. So we're going to say positive 10 for dy over dt. And for the r value, that's the distance at this time between the two ships. You actually found that in part A. That was 5. But you could use Pythagorean theorem again if you needed to. And then dr over dt, again, that's what we're solving for. All right, let's clean this up a little bit. So over here, this is going to be, let's see here, 4 times negative 15 is negative 60. Times 2, we've got negative 120. And this is going to be a big fraction, by the way. I'm going to divide all the stuff over here by 2 times 5. So we've got negative 120 plus, this is 60, all over 10. And if I put units on the end of this, I'm actually done with the problem because this is all constants. But I have a hard time not simplifying this, especially if I'm not actually at this moment taking an AP exam. So this is going to be negative 60 over 10, which is going to be negative 6. And this is going to be in kilometers per hour. So there we have it. For this problem, we're trying to figure out the change in theta now in radians per hour when x is 4 and y is 3. So this is another related rates problem, like part B, but this time around we have the relationship between the rates of change of these two quantities and the rate of change of the angle itself. So this is going to require a different formula to tie everything together. Since we're talking about the angle on a right triangle, this is going to be one of your SOHCAHTOA relationships. We have the opposite side and the adjacent side with respect to this angle. Opposite over adjacent, that's going to be tangent, TOA. So we can write tan of theta equals y over x. And if we go ahead and take the derivative with respect to time of all this right away, we are going to run into a little bit of an issue. We're going to have secant squared of theta times d theta over dt. We're solving for d theta over dt. The trouble is figuring out theta when x is 4 and y is 3. That's going to be a little bit dicey because we don't have a calculator to work with. So instead of dealing with that, I'm going to take my chances and take the arctan of both sides of this to get theta by itself. So I can write theta equals arctan of y over x. And if I do that, when I take the derivative now, I'm just going to have a d theta over dt on the left side here. So I'm not actually going to have to figure out the value of theta at all. I'm just going to have to know what x and y are, which I already know. So d theta over dt then is going to equal, well, this is going to be kind of crazy over here. We have a chain rule with a quotient rule built into it. So this is going to be a little bit gnarly, but again, this saves me the trouble of having to calculate theta without a calculator. So we have arctan of something. That's the outer function here. The derivative of that on the outside is going to be 1 over something squared plus 1. So in this case, 1 over y over x squared plus 1, which is a little bit annoying, but we can do it. Now we have to multiply by the derivative of y over x. That's going to require a quotient rule. So let me set up my box and ribbon here. I've got my numerator, which is y, my denominator, which is x, and the derivatives of those, which are dy over dt and dx over dt. Now, note that I know all of these quantities in this problem, so this is a good thing. So now multiplying these out with the ribbon, we've got u prime v, so x times dy over dt, minus uv prime, so y times dx over dt, all over v squared, so all over x squared. Okay, time to start plugging stuff in. So in the numerator, I'm going to just plug stuff in right here. I have an x value of, they said the x value is 4, so we've got 4 for x. dy over dt, again, that's the rate of change for this ship, which is sailing away. So this is a positive quantity. This is 10 again, and we saw that in the last problem, the last part. So minus now the y value they said was 3, and dx dt, we said this distance was decreasing, so this was negative 15 kilometers per hour in there. And downstairs now, we have y over x, so that's going to be 3 over 4 squared plus 1. And we also have x squared, which is going to be 4 squared. Now, we could stick units on this, which is going to be, they told us here, radians per hour. And actually, you'd be done if you put units on here and just moved on with your life, because this is all constants at this point. But if you absolutely feel the need to simplify, we can do that. So upstairs we have 40 plus 45. Downstairs, well, this is going to be interesting. We've got 9 over 16 plus 1, which is 9 sixteenths plus 16 sixteenths, which is 25 sixteenths, times 16. And simplifying a little bit more, on the top we have 85. Down here, these 16s cancel, leaving us with 25. We can reduce this by 5s. So this is going to be 17 over 5. And again, that's going to be radians per hour. So there it is.